So hello everybody. My name is Alexandra. As mentioned, I am working with Dr. Russell White. We've been looking at a bunch of young stars a lot closer by than everybody else. So yeah, big shift. We're just looking at a bunch of galaxies. Now we're just looking at a little nebula and a bunch of little stars, and they're only roughly 400 parsecs away. That's like 1,300 light years. They're like right next door. So let's take a look. Just a general topic list. I'm going to tell you about the Dunn Nebula. I'm going to tell you what, once again, spectroscopy can tell us about, this time, young stars, and about star formation. So, a quick overview. So, how do you make a star? Well, you start out, I guess let's come over here. You start out with a big bunch of gas and dust. Then you wait for a while, and eventually the self-gravity acts on it. You just collect all that gas and dust together until you form a little dense cloud core in there, just denser and denser. So eventually it all sort of spins together and you get a little star, a little pulsar in the middle of the end of the finger of the mechanical somewhere. So they'll spread out into the distance. It should kind of resemble a solar system. And in fact, hopefully it forms with you. And then by the time the young star eventually flows away all the extra gas and dust, our stars aren't here yet. They're like somewhere in between. They're young. They just started fusing. It's only been maybe a few million years. It's a star. That's very, very early in its life. So we're going to the Dunn Nebula. You can actually see it from here. I checked. If you look due south, about 20 degrees up at 7 or 8 p.m. tonight, you can point towards my stars and say, they're right there. You won't really see them. They're quite faint. Visual magnitude 15, 16. You can see all the way up to 6, okay? So, like, these are very faint. You probably won't see them unless you're superhuman. But they're there, I promise. They're in the constellation Vela and Puppis. Ours are actually in Puppis, but that's the region. The whole Dunn Nebula kind of spans both of those constellations. It's a 40-degree diameter nebula. That's like 80 times the size of the full moon. It's a pretty broad area, but it's very faint. So it's big, but it's faint. It's really actually hard to see. It's also in the galactic plane, as you can see. That's the Milky Way going right through it. So it's a bit of a pain to study, too. That's probably why it's not as well studied as some other young star-forming regions, just because there are a lot of background stars. But we went on with it anyway. So some other stars in the region, there's some bright O stars, bright B stars, particularly Zeta Puppis, Gamma Boron. This doesn't all matter. Anyway, these are the main energy source we're thinking for this region. They're probably what's actually lighting it up. Okay, so zoom in a little bit. These are our 10 targets. They're all circled, they're all labeled. These are all young stars. They were studied by Pedersen. One object of interest, though, is all the way over here. This is called cometary globules. You see some people on those here. You can see blob of gas and dust. So it shoots out into a comet shape. It's not an actual comet, it's just comet shaped. And you haven't observed them anywhere else except in the Dunn Nebula. So it's a very special little object. We're actually going to take a closer look at ours. It's circled. There's a little red dot inside it. So it's an infrared source. People have seen there's something in there. We don't know quite what it is, or at least they didn't before. We've gone and checked it out. It is really a young star. So apparently these mysterious cometary globules are a lot like any just clump of gas and dust. They can have stars inside them. We know because of course, high dispersion spectroscopy. What did I just say? Something we've been hearing about all day. So high dispersion spectroscopy. This is just really good spectroscopy. It just means you get a lot of detail in your spectrum. You do that by just using a really big telescope and a really good spectrometer. We used the one in Keck in Hawaii. I didn't do it, my professor did. But yeah, it's very good data. As you can see, it's really quite clear. So here's an example of it. Here are all 10 of my stars. It's, a little noisy, but it's not bad. You can see a lot of what's going on. So what can this tell us? We already kind of know this. You've already gone over it in class. The lines that you see there, the strength, how deep they are, that's going to tell you how much of each element is in each of these stars. So here we see a bunch of calcium in the first column, iron, et cetera, et cetera. The second column is kind of interesting. That's lithium. So that's three protons, isn't it? So that's an element of interest because it I'll get to that, actually. Let's just go over the other ones first. So in the middle column, you see a bunch of really deep dips, right? Those are actually from molecules, titanium oxide. You see those in a lot of cool stars. So yeah, again, we're already finding out the spectra can tell us a lot. It can tell us what is a star, it can kind of tell us what kind of star it is. We'll see more of that in a moment. Let's talk about lithium. So lithium. Everybody's used to stars fusing hydrogen, right? That's the one everybody talks about for the sun. It's what characterizes the main sequence. Stars spend most of their stable lives taking hydrogen and mashing it into other hydrogen atoms and eventually building helium. But lithium, it turns out, you can smash that into a proton a lot more easily than you can smash protons together. So you only need to be at 3 million Kelvin for this, as opposed to the usual 13 million Kelvin you need for hydrogen fusion. What this means is a young star can start fusing lithium into something else. In this case, it ultimately ends up as 2 helium atoms. That can happen a lot sooner than the hydrogen. And once you get to hydrogen fusing temperatures, the lithium just goes like that. It goes immediately. Almost. Okay, by immediately I mean like 10 to 20 million years if you're an M-type star, so a very cool star. It'll take a little longer for a larger star like a K star. Okay? But the point is, if you see lithium, and we do indeed see lithium, look at how deep that is, right? You see what is that? It's a cooling star. But it's something flat. Look at these big lithium dips. There's lithium there. There's a lot of lithium. That means that this reaction that proceeds so fast hasn't had a lot of time to operate yet. So these stars are very young. Okay. So what else can spectra tell us? Well, you've heard a lot about this. It's the Doppler shift once again. In this case, we're not really using it to gauge like how is the universe expanding or anything, or even really how fast are the stars moving away from us. We are, but what we're most interested in are these stars moving away together or not. It's more of just do these objects that look close to each other actually move around together? Are they dynamically related? That's all we're really interested in. We've already kind of gone over how the Doppler shift works, so let's just look at what we found. The 10 stars that I've been looking at, here they are just plotted just with their coordinates. Just if you were to take a map, this is where they are next to each other. They look close together, and they probably are. They're in a range of just several kilometers per second of each other. It's reasonable to assume that they're probably moving together. We think it's one population of stars. Just got to double check that before you go too far. If you're dealing with two completely separate, just going totally different directions, they might not be related. You might be able to talk about them as two separate populations, for example. But we just have one. Makes things simpler. All right, what else can we find? We can figure out how fast these stars are rotating. And this becomes kind of interesting. So we're used to Earth spinning, right? That's why we have day and night. Turns out if you watch the sun, you won't notice anything. Don't watch the sun. But if you put a filter on your telescope and you look at the sunspots, you could see one earlier, right, just outside. If you watch those sunspots long enough, you'll see it drifts along on the surface slowly. That's because the sun itself is rotating. Turns out all those stars out there, just like a lot of things in the universe, are actually spinning. So it's nice to know how fast they're spinning. You can tell how fast they're spinning by looking at the shape of the absorption lines that you've been looking at. So the faster it spins, the more Doppler shift you get, and that's going to spread out any light that's coming at you into a broader set of wavelengths, basically. So, yeah, you end up getting this, right? So instead of just a little skinny, you get it kind of broad and shallow. You can actually quantify that to figure out how fast your star is rotating. If it's rotating about 10 kilometers per second, that means that you're dealing with a fast rotating star. So ours are pretty fast. This is sort of a lower limit of how fast they're rotating. We don't really know which way they're pointed. Anyway, it's, as you can see, even 8 kilometers per second is the lower end of how fast they're rotating. It's pretty fast, and it goes all the way up to 28 kilometers per second. That's also, in fact, an indication that these stars are young. And here's why. A lot of stars, especially for what size we have, they're convective. They have all this gas and dust, charged gas, I should say just charged gas moving around inside them. That's going to create a magnetic field. If you have that big magnetic field and you try to spin it, and you have all these stellar winds, which is also kind of magnetic activity trying to move through that, But ours are still really fast, which means they haven't had a lot of time to slow down. Which means, again, they're probably not. You really have to check carefully this is how so galaxies eat gas, there's stars eat gas too, on a much smaller scale. So there's increasing as well, and whenever they eat gas, they also light up. Just kind of like the big galactic nucleus. They also give off some extra light, they give off some additional light. And you can also categorize how bright is it, how fast is that gas moving into that star. If it's moving really fast, I mean, this probably draws a lot of extra gas. And this is some run stars off. It's relatively broad there. Another effect of that is as the gas heats up underneath the star, it's going to give off a lot of this extra kind of featureless light. That's going to make all the little atomic lines that are like a little shallow. So whenever you see that little shallow line, there's a better picture on it here. Whenever you see, so like this is our star, right? One of them, we have a bunch. This is a standard star, just a regular middle-aged type. You can tell that these lines for our star are a little bit shallower. Whenever you see that, you can say, there's a bunch of gas that's falling off the star and heating up. There's what we call veiling. That means the star is accreting. So whenever you see some shallowing, consistent shallowing like that, it could be related to rotation, but it can also be a sign of accretion. You just start filling gas. I need to fill out a disk around it. Yeah. Alright. So, yeah. Spectroscopy stuff, right? What else we can get from spectrum? We get the spectroscopy stuff. On the 60 pair, I've already kind of mentioned that they're M stars or K stars. They're very cool. I'm sure the G star, that's what the next class up has K everybody did. So these are fairly cool right now. They might be up a little bit as they age, but probably not be harder than we make some corrections. This stuff really nitty-gritty. It turns out there's a lot of gas and dust floating around in space, especially by a young star, right? They're born in this stuff. What that's going to do is, when we get to the picture of the star, your spectrum, it's going to make that star look dimmer than it actually is, not so redder than it actually is. As I mentioned earlier, that gas and dust will be scattered, especially the blue light, leaving you with a redder-looking, dimmer-looking star than it's supposed to be. So we want to know what the star is actually like. We want a true picture of the star. We want to get rid of all that extra reddening, right? So there are ways to do that. Since we already know that we have N and K type stars, we can compare the stars that aren't there, and then kind of correct for the fact that aren't on it. We can sort of add back the light that it lost to this gas and dust. And then we can get a better picture of what the stars are doing, what kind of stars they are, and what they might do in the future. Okay. Especially what we want to do is we want to get our intrinsic lighting. It's a really big application. As soon as I get to the next level, everyone's like, oh, it's this again, right? So, yeah, each star, it pumps out only so much light. You move the far away, it looks different, quick stuff, and then it looks different. We want to know how bright is the sun? By removing all that dust, and then by guessing a distance, we can figure that all out. Meanwhile, we also know the temperature of the star, right? Because we already have spectrum type. I already mentioned it's pretty cool and stuff. You get an idea of that just by looking at the line ratio. But that's more complicated to get into. It's just another channel over here. HR diagram, right? Somebody knows what to do with that. You got the temperature, the color of the star, you have the temperature, you have the brightness, and it turns out, for a middle-aged star, you get this nice thick line, right? All the middle-aged stars, they kind of all go to here, and then they stay there for a long time. That's the main sequence. Hopefully you're all familiar with that. The main sequence, that's the stars spend most of their life. How can we get our stars like at such and such temperature, so they stay there for a long time? Our stars are young, we think. How young? Well, we're not quite sure because, well, we are sure a little bit because of other issues, but from the HR diagram, it's a little tricky because besides the resonating on that, like I mentioned, yes, you know how far they are. They'll look a lot brighter if they're close enough. So they'll actually be, they'll look bigger if far away. So you know how far away are they actually. This is just a guess, 200 plus, but that's actually kind of low. This is a better guess, but I just want you to see. That distance that we pick, what's that? Makes a big difference, doesn't it? But even though I'm going to talk like this because that seems to be how some people think about Nebula, and that's where we do our stuff. So it seems to be a good guess, and it goes well with lithium estimates. We're pretty sure our stars are relatively young. So let's see, that's like 1 million years, that top line. And this would be 10 million years, this middle line. They're kind of spread around there. Maybe this guy's here, maybe this one. But most of them are pretty young. We bet. Okay, that's our research so far on our 10 planet stars. We want to study more in the region, and here's why. Remember all that Doppler Shift stuff? How long was this one? It was some follows. If you dig along this, there could be so many answers along this particular star in the area. Now, it has a big name called by that for short. So this RF star is supposedly 3,400 miles away. Okay, so it's how far is it? More than 10,000 miles. They think it's far because it's next to some H2 region that they think is about 4 miles away. It looks like it's close to it, it might be related, you know, you kind of guess. But if it's really that far, that means this star would have to be 24,000 times as far as the sun. Which is possible, but not really for the kind of stuff that this is, because it's an F star, which is just the next class higher than the sun. So it's a little bit harder than the sun. We should be able to do that, but that's sort of suspicion. We think it might actually be related to our group of stars. I mentioned that they're all moving as a group 20, 30 kilometers per second away from us. Turns out this guy's moving at about that speed, so it might be related to our star. If it is, then it comes down to a much lower luminosity, 330 times better than the sun. That's a lot more manageable. That might actually be possible for an star. So we want to do a bunch of tests like that with these. We're hoping to maybe even observe red, hopefully, if I can get it supposedly. That's going to tell us whether or not several red objects in that area may be also known stars and actually closer to the system. Yeah, we also maybe map the whole region to figure out all the other stars in the area. There might be some moving in different directions. We want to know everything that's going on there. We'll just observe some more properties of them stars. That's really our whole goal. And I think that's really all you guys really need to know. In case you want to find it, that's how you find it. And yeah, go to Spectroscopy. This is the main conclusion of today. All right, we'll give her a hand.